Gentlemen, we're going to be talking about linear approximation and error. And linear approximation is literally a line that approximates a function at a particular point. So what you're going to use is you're going to use linear approximation. Literally just allows you to approximate a line, an approximate function that's not a line, with a line. So as you're really, really close to something, and that's where that really, really close piece comes into play. If you're really, really close to a particular value, you can use, and you zoom into that particular value, you can use a line to approximate the function, because the function will kind of look like a line. Even if it's curved, as you zoom in closer, it looks like a line. So a tangent line approximation is literally that equation. So let's start on equation number 1. So y minus y1 equals m times x minus x1. Equation of a line, where m is the slope and x1, y1 is the point. Well, we're going to call my point, we're going to call my point a comma f of a. We're going to compare that. So the x value is a, the y value is f of a. If that's true, then this equation becomes y minus f of a equals m times x minus a. Plugging in the point for x1 and y1. Well, if we think about this, what does m represent but the slope of the tangent line at a particular point? So can't I rewrite this then as y minus f of a equals f prime of a times x minus a. So again, I now replace the slope with the derivative because that represents the slope. Can I solve for y is the question. And if you look at this, y equals f prime of a times x minus a plus f of a. Ladies and gentlemen, this is linearization. L of x equals f prime of a times x minus a plus f of a. A right here. And what this is saying, ladies and gentlemen, is that you have an x value and a is really close to it. Okay? You have an x value and your a is really close. We want to approximate. So the differential, when we talk about, this is linearization, a differential is a derivative, or a change in y, or a change in x. It's that derivative, that change in. Okay? So do a change in y, change in x, delta, y. We're going to talk about relative error and percentage error in a minute. That's later on. But we'll talk about these 4 things right here. And that's not get lost. So here we go. So again, ladies and gentlemen, if you think about it this way, here's my equation again. Y minus y1 equals m parentheses x minus x1. If you think about this, this is delta y. We consider it the error because it's the difference in y. It's how much y is off. And if you think of this one, this is delta x, or the change in x. It's the error where x is really small. The whole point of this is that a and x are really close to each other. That's the whole point. Is that difference is going to be different. It's going to be small. So again, we have y equals f of x. So again, this is literally what you had before when I solved for y. That said, f prime of a, because this was y minus f of a, y minus y1 equals m, which is f prime of a, because that's the slope at that point, times x minus a, or f prime of a times x minus a plus f of a. There's y equals. And here's the whole point, ladies and gentlemen. If you look at my picture, here's point A. That point A is on this nice pretty curve. There's my nice pretty curve. But if I was to zoom in really close to this point right here, if I was to zoom in really close into where this box is, would this not curve, not look like a line. And the whole point is, if I can approximate, I'm going to use a line to approximate, because I can find a line easily. I'm going to use that line to approximate that curve. And it doesn't matter how steep this curve is. I mean, this curve could be like this. It could be, like I'm talking about the point like right here. It doesn't matter what point I'm talking about. I can zoom into that point and make this look like a line. Okay? So we are approximating the new y value. We're not finding the exact value of the curve. Okay? And as long as your delta x is small, so as long as your a value is close to the x value that you want, then you're okay. So let's talk about what this means. And we are going to talk about having overestimate and underestimate in a minute. We're talking about that concavity and stuff like that next class, but overestimate and underestimate. So is the curve above the line, or is the curve below the line? If the curve is below the line, I'm sorry, if the line, I should say that better, if the line is above the curve, then that's going to be an overestimate, because it's above the line. If the line is below the curve, then that's going to be an underestimate. Now I'm not going to use the line that goes here, where this green dot is, to approximate something where the red line is. Or to approximate something where the blue dot is, because those aren't close to each other. If I'm going to use this line, I'm using my blue dot like right next to it. Okay? Or I'm going to get my purple dot. So I could use the line, the green line to approximate the purple dot. I could not use the green line to approximate the blue dot, because they have to be really close to the values that I have. Alright, so here we go. And again, you can see my tangent lines are overestimates and my tangent lines are underestimates. So here's the deal, and you can see it right here. Use linear approximation of the graph of 1 over x to estimate one of the value of 1 over x, 1 over 10.2. So find the exact value with your calculator and see how good you are. So I'm going to write this on another page to make it easier on myself, because we know that that's not that close. And so I need a much better page. So there we go. F of x equals 1 over x. And I want to approximate 1 over 10.2. So here's my question. First of all, the first thing that I'm going to write down is what's the formula. L of x equals f prime of a times x minus a plus f of a. Here's something that you didn't know. A is a value that you know and can easily find. A is a value that you know and you can easily find. And usually it's one that you have to figure out what you're using, but it is something that you can easily find. So in this case, if I'm looking for 1 over 10.2, and this is what I'm looking for, 1 over 10.2. 10.2 is really close to a whole number that I know, because usually I like to use whole numbers. So I'm going to say let A equal 10, because that's close to 10.2. So if A is 10, f of A is going to be f of 10, which is 1 over 10. That's something that I know. I can do that. Let's talk about what f prime of x is. Okay, talk about f prime of x, and I need that. Because again, I am filling out this right here. This is what I need to fill out. So I've got f of a. I know what a is, and now I need to find f prime of a. Before you find f prime of a, you have to find f prime of x. F prime of x is going to be negative 1 over x squared. Because x is negative 1, x is negative 2. So therefore, f prime of 10 is going to be negative 1 over 10 squared, or 1 over 100. So my linear approximation is going to look like this. L of x is going to equal f prime of 10 times x minus 10 plus f of 10. Because 10 is my A value. So f prime of 10, negative 1 over 100 times x minus 10 plus f of 10, which is 1 over 10. There's my linear approximation equation. Sometimes I ask for a linear approximation equation, and sometimes I ask for using it to approximate something. Sometimes I just ask for the equation. Or it says write the equation and use it to approximate. If it's write the equation, I still have to see this with x's in there. Now, I'm going to do L of 10.2. Because that's what I want to approximate. So negative 1 over 100 times 10.2 minus 10 plus 1 over 10. Now here's what you really need to understand. This piece right here, that's highlighted in blue, that better be really small every single time. That parentheses better be a really small number when you're evaluating. It has to be a really small number because that's the two x values. Those are your two x values that you're talking about. So the distance, that's your delta x. That delta x has to be small. And it is in this case. That's why that has to be really small. In our case it is. So L of 10.2 is going to be negative 100 times 0.2 plus 1 over 10. Negative 100, 2/10 is 1/5 plus 1/10. Which makes this negative 1 over 500 plus 1 over 100. Our denominator makes this negative 1 over 500 plus times 5, so 5 over 500, which makes this 4 over 500, or 1 over, I have to do math in my head. 1, 2, 5. So, L of 10.2 is approximately 1 over 125. Well, F of 10.2 is 1 over 10.2. Let's see what that actually is. So let me fix something, because I just realized it went from 1 over 10 to 1 over 100, so let me fix that. So if I can do 1 over 10, that's 1 over 10, which makes this 50 over 500, which makes this 49 over 500, so that's much better. Sorry about that, guys. And so that's 49 over 500, so this is approximation. Please note that I have the approximations over there. I have 49 over 500. And now if I look, wrong thing, there we go. I'm going to do 49 over 500, gives me this decimal, 1 over 10.2. Because I do forward, hold on, I do 449 now. Oh my goodness, this zero cannot type today. 500. Leave that 0. There we go. And you'll notice I am pretty daggone close. I am at 0.098031, and I'm at 0.098. 3 decimal places. That's pretty daggone close. So it's a way for me to approximate something with not actually having any values, because I don't know what 1 over 10.2 is, but I can do that math. I can do the linear approximation and make more sense. So, using the example 2 says, using the tangent line for tangent line to y equals the cubed root of x at x equals 8, estimate the value of the cubed root of 8.2. Okay, so is this a value an overestimate or underestimate? So again, I'm going to do this on another sheet, just to make it easier. Y equals the cubed root of x and x equals 8, and I usually won't say that, and I want to find the cubed root of 8.2. By the way, I usually won't say this piece, so you need to figure out what A needs to be. And it says that x equals 8, that's the value that I know. I can do the cubed root of 8 easily. That's the whole point of this, is that I can do the cubed root of 8 easily. I don't need 9 because I don't know what cubed root of 9 is. It's some of the value that you can find easily. So again, I'm going to write my formula. It says L of x equals f prime of a times x minus a plus f of a. F of a is going to be f of 8, which is going to be the cube root of 8, which is 2. I also need f prime of x, which is 1/3 x to the negative 2/3. So f prime of a is going to be f prime of 8, which is 1/3 times 8 to the negative 2/3, which is 1/3 times 1 over the cubed root of 8 squared. The cubed root of 8 I can do, I'm actually going to do that first. The cubed root of 8 is 2, and then 2 squared is 4, which makes this 112. The only reason I did the cube root first is because, yes, you know what a squared is 64, but if that was like 27 squared, I don't know what 27 squared is, but I know what the cube root of 27 is, and I can do 3 squared. So that's the whole point of doing it that way. So now I have all my information. L of x, f prime of a, just write it again so you can see it, x minus a plus f of a. So L of x equals f prime of 8 times x minus 8 plus f of 8. F prime of 8 is 112 times x minus 8, f of 8 is 2. Here is my equation of tangent line. Find the equation of tangent line and then use it. There's my equation of tangent line. Now I'm going to use it. L of 8.2, 112. 8.2 minus 8 plus 2. 112.2 plus 2. 112.2 is 2/10, which is 1/5, plus 2. 1 over 60 plus 2 makes this 121 over 60. L of 8.2 is approximately 121 over 60. And you can check. The cube root of 8.2 is approximately the same thing. And you can check that. I'm not actually going to show you the check for that. We also have to decide if this is an overestimate or an underestimate. So let's talk about what the cube root of x is going to look like. When I think about the cube root of x, it should look something like this. By the way, the first positive at 0. But it looks something like this. And 2, at 8, x equals 8, I'm over here. Okay, now I am above, that graph is going to be above, so that means this is going to be an overestimate. Because that tangent line is going to be above the graph. That's the question, is the tangent line above or below the graph? Alright, so let's go back to the next problem. That says, example 3 says, find the approximation. Actually, and I'm going to skip that one. I'm going to use, I'll do example 4. Find the local linearization of y equals sine x at x equals 0. Actually, yeah, we'll do that one. Okay, so, for example 4, it says local linearization of y equals sine x at x equals 0. So, y equals sine x, and I want you to find approximate sine of 0.01. So, okay. So A is going to be 0, because that's really close, and I know what the sine of 0 is. I don't know what the sine of 1 is, so I'm not going to use 1. I don't know what the sine of 1 is. I know what the sine of 0 is. A is 0. F prime of x is going to be cosine of x. So, f of 0 is going to equal the sine of 0. 0. That's f of a. F prime of a is going the cosine of f prime of a is going to equal f prime of 0, which is the cosine of 0, which is 1. So L of x equals f prime of 0, which is 1, x minus 0, plus f of 0, which is 0. There's my local linearization line. So now I'm going to use this to approximate the sine of 0.01. So the difference between 0 and 0.01 is 0.01. 1 times 0.01 minus 0 plus 0, 0.01. L of 0.01 is approximately 0.01. So the sine of 0.01 is approximately 0.01. If you look, sine of 0.01 is 0.009998. That's pretty daggone close. So yes, I'm pretty daggone good. So local linearization is nothing really new. It's like literally the equation of the tangent line, but it's using it to approximate something that I don't know. So let's skip ahead. Okay. No, actually, I'm going to do example 9, and then I'm going to skip back. So example 9 says, the approximate value of y equals the square root of 4 plus sine x at x equals 0.2, obtained from the graph at x equals 0 is blank. So now that's what I'm going to use. And I'm going to do it right here. Ladies and gentlemen, A is 0. Nobody writes that. So f of A is f of 0, which is the square root of 4 plus the sine of 0. The sine of 0 is 0, so that's the square root of 4, which is 2. So I got f of A. Let's talk about f prime of x. F prime of x is 1/2 4 plus the sine of x to the negative 1/2 times the derivative of the inside, which is cosine of x. But I want f prime of A, or f prime of 0, 1/2 4 plus the sine of 0 to the negative 1/2 times the cosine of 0. I'm going to come down here, clear right on the room. So that's 1/2 4 to the negative 1/2 times 1. 4 to the negative 1/2 is 1/2, so this becomes 1/4. So my equation, L of x, becomes 1/4 x minus 0 plus 2. Ladies and gentlemen, the difference between 0 and 0.12 is 0.12. So now I have L of 0.12, 1/4, 0.12 minus 0 plus 2. Ladies and gentlemen, 4 goes into 0.12 because that's a decimal, that's 12, which makes this 0.03, because 12 divided by 4 is 3, 0.03 plus 2, or in our case, that means my answer is 2.03. So you see how we're using local linearization. It's decimals, but I can do those decimals. Those aren't bad decimals for me to do. Alright, so now the last thing that I want to talk about is relative error and maximum error. And let me find my paper for that. Hold on 1 second. Sorry, so it's over here. So, relative error and maximum error deal with the differentials, deal with delta x's. And so in this case, we're going to talk about the radius of a circle disk and a maximum error of measurement. So give me 1 second to get to a new page, and then we'll talk about this one. Okay. So for this one, let's talk about what this picture represents. A radius of a circular disk is given 24 centimeters. So R equals 24. With the maximum error in measurement, so delta R, how much could it be off by? It's 0.2 centimeters. Ladies and gentlemen, that means that I could be at 24.2, or I could be at 23.8. That's what it's saying for maximum error. So I'm saying that R should be 24, but reality check is R may be 24.2 and it may be 23.8, because those are between 23.9. The maximum error is 0.2 centimeters. So now we're going to talk about our differentials. Well, estimate the area, calculate the area of a disk. Well, area from known as area equals pi r squared. Everyone okay with that? Hopefully you are. Let's talk about differentiating this. Ladies and gentlemen, when I'm differentiating this, I'm not going to call it A prime, I am going to call it dA dr. There's a reason for that. dA over dr. It is the same thing as A prime, but you're really going to want to write dA dr today. dA dr is equal to 2 pi r. So the derivative is 2 pi r, like this. Well, ladies and gentlemen, if I write it as dA over dr, dA equals 2 pi r dr. Ladies and gentlemen, if you look, these right here are your delta x's and delta y's, or delta r's and delta a's. They're your change-ins. There's your differentials. So if those are my differentials, then I can find out what kind of error that I'm going to have. The error in the area, because what this is saying is that my rate of my change of my R value could be as much as 0.2. But I know what my R value is, so I can actually change that R to 24. So now I can do this math. And I know that if my radius is only changing by 0.2, and I do this math, that means that my area could be off by as much as 96 pi. This is centimeters squared because of area. That's what this is, the differential, the error that could be off by the area. Now, let's talk about this is like your maximum error. This is your maximum error, because this is the error that could happen, the max amount of error that I could be off by. So now the question was, I'll go back to my question. The question was, what's the relative error? And here's how you figure out the relative error. Here's how I always say it. The relative error is your data error, or I call it my error, over the max error. Or the max, I'm sorry, not max error, max area. Nope, I'm right, sorry, I was right, max error. So my data error is 0.2, because my relative, because I can be off by 0.2, over 96 pi. And so I could do this as a percentage. So it's my error of the max error. So 0.2 over 96 pi. And I can do the percentage, and that's my percentage error. Okay, sorry, I thought I said something wrong. I did. It is not, I said this wrong. It is not the data. It is my error. Let me fix this. That is totally wrong. Relative error is the max error over the total of whatever you're talking about. Area, volume, etc. The total volume, think about this, the total volume, total area for this problem would be pi times r squared. Total area, pi r squared. And so my relative error would be my max error, which was 96 pi, over 24 squared pi, or 96 over 24 squared. I don't know what 24 squared is. 24 squared. And I have 96 divided by 24 squared. So the relative error, while that looks like 96 pi looks really big, reality is 0.1667 or 16%, 16.667%. 16. you would be off by. Okay? So while 96 pi sounds really big, in the grand schemes of how big it is, it's not that big. Okay? So now you're going to have more problems with these to work on. We will talk about these next class. We'll spend probably about half the class talking about related rates and then this stuff. You do have a worksheet for homework because WebAssign is still not working, so you do have a worksheet for homework. Thank you. Have a great day.